Okay, good afternoon. So today is actually, if it's sort of part of last week, we're still on the topic of trees in a way. I'm on page 306 in the reader, if you want to follow along. We're going to be talking about the Scheme 1 interpreter. It's a little scheme interpreter. So there's this progression from the calculator that you saw a week ago that only does arithmetic and doesn't have variables. And now we're going to look at one that implements the substitution model that you learned about back in chapter 1. And then when we get to chapter 4, comes the sort of real, sort of full strength, the way scheme really works, metacircular evaluator. And the reason we're building up to it is that traditionally students have found the metacircular evaluator hard. You know, chapter 4 is said to be a lot harder than everything else in the course, and so we want to get you prepared gradually for it. Okay. So why write a scheme interpreter in Scheme anyway? What's the point of doing that? It seems a little weird because you can't run it unless you already have a scheme interpreter to run it on, so why not just use that? And there are 4 reasons. One is having an interpreter to look at, to read the code of, helps you understand the model of evaluation. So when we say something like Scheme uses applicative order, which you learned back in the first week, or Scheme uses the substitution model evaluation, or something like that, you can really understand what those things are saying by seeing in detail written out what that means. And so we're going to be doing that today. Second thing is it lets us experiment with modifications to schemes. So when we get to chapter 4, we start with the scheme interpreter. And then in the book, there are 3 different modified versions of the scheme interpreter that we're going to look at and see how we can change the language by changing, not very much in some cases, of the code of the evaluator and why you might want to make those changes or might not. A third point is that even real industrial scheme systems are largely written in Scheme. Typically, there'll be a tiny core of things having to do with storage allocation that are written in some lower level language like C or Java or something. And then most of the work of being a scheme interpreter is written in Scheme using code that's not so different from what we're going to be doing. So this really is how it's done. And there's this bootstrapping process where you use some other interpreter or some other system to get going in the first place, and then you sort of use your own interpreter to interpret the scheme code that's part of the interpreter. So this is not so unrealistic what we're doing. And lastly, looking at an interpreter for a programming language, any implementation of any programming language conveys one of the big ideas of computer science, which is universality. So I want to start, even though it's kind of abstract and up in the air, by talking about universality, which is what this picture is about. On the left, what you have is a function machine. You probably saw these for the first time in Algebra 1 in 7th grade or 8th grade or something. And there's a crank on the side of the machine, and you put in numbers, and other numbers pop out the bottom. So this is x maps to 3x plus 7, and I put in 5, and I got 15 plus 7, which I hope is 22. And that's a machine that computes a particular function. Machines like this have been around for 2,000 years that I know about. The ancient Greeks had machines like this that computed particular functions. They used them for things like showing all the heavenly bodies revolving around the earth, back when people thought that. And also for navigational problems and so on. So machinery to compute particular functions has been around forever. But the thing that made possible the computer era that we live in, where you have things like iPods and GPSs and all of these myriad computer devices, is going from this model where a particular problem is built into your machine to this model where there's a universal function. In the book, in chapter 4, when we do the metacircular evaluator, they use the yin-yang symbol to represent the metacircular evaluator because it does mutual recursion, as we'll see shortly. And this universal function takes as its inputs first a description of a machine. So we take this machine, we make a description of it in some programming language, like we say lambda of x plus times x3, 7, or something equivalent in other languages. And that goes in here, and then whatever data you want as inputs to that function, and crank, 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 and out comes an output. So you only have to build one machine that can do anything. So the thing that's new in the computer era that started, maybe 70 years ago now, is the notion of a general purpose computer, where the action that you want to do is represented as data, just like the numbers you want to work with are represented as data in the machine. And that was a huge idea. We've seen that idea before. That's what lambda is. When we did higher order functions, we were taking programs, actions, descriptions of actions, and using them as inputs to other functions like map and filter and so on. And that's the idea of universality. So programming languages are a piece of that. And it's an important reason for studying something like an interpreter. OK. Well, I should say a programming language is the software version of this idea. It's this idea in hardware that started the computer era. But also, pretty shortly after that, people started inventing programming languages. So instead of having to represent your problem in the language that the machine knows, you can use some more abstract language. And that contributed to universality in the software arena. So it's writing one program that knows how to do any computation. That's what an interpreter is. OK. Up on the screen is the one screen-full version of a scheme interpreter. And first thing I want you to notice is that it looks a lot like the calculator program you saw last week. The calculator program had 3 parts, and here they are. The first part is the read eval print loop, which basically hasn't changed. And the second part is eval takes an expression, which is a piece of text in the programming language, and returns the value of that expression. And then finally, apply, which is out of the realm of what the programming language looks like. So there's no expressions in here. Apply takes a procedure and argument values and calls that procedure with those arguments and returns the value that that procedure returns. And those are the pieces of, if you sort of step back and squint, any interpreter for any programming language basically has those pieces. This is one reason why Lispians like to say, inside every language, there's a little Lisp hiding. OK, so what kinds of expressions are there? In the calculator program, let me just remind you, an expression was either a number or it was plus, minus, times, divide expressions. So expression is defined recursively because these spaces can be filled in with any expression. But those are the only kinds of expressions that there are in the calculator program. In Scheme, we divide up expressions into two kinds and then each of those into two kinds. So an expression is either an atom or a list. Now that's sort of a tautology because the definition of atom is something that isn't a list, or more precisely, something that isn't a pair. So something in scheme that's built up out of pairs but isn't a list is not an expression. There's no category for improper lists, or dotted pairs, as people say. Now, there are two kinds of atoms. They are self-evaluating so that's numbers, same as in the calculator program, are self-evaluating, but so are, for instance, hash t and hash f for true and false. The value of hash t in scheme is hash t. And so are strings in double quotation marks are self-evaluating. And there are a couple more things that are self-evaluating. And symbols, which are the names of variables. That's an A. Sorry, I have lousy handwriting. What can I say? If an expression is a list, there are two kinds. And they are procedure calls and special forms. So it's a special form if the car of the list is a keyword. Keywords are the names of special forms. They're things like lambda and define and if and cond and so on. So if the car of a list is a keyword, then the list as a whole is a special form that has special evaluation rules. Otherwise, if it's anything else, it has to be a procedure call. So in my evaluator, my tiny evaluator, I say, well, if the expression is self-evaluating, then just return exp, the expression itself. That's what self-evaluating means. If it's a symbol, then we just look it up. And in the substitution model, we're never going to get to eval with a symbol as the expression unless it's a global variable. Because local variables, the ones that are formal parameters of procedures, get substituted out before we do the evaluation. You'll see that in a bit. So it's look up in a list of global variables this variable name and get the corresponding value. If it's a special form, that is, if it's a list and its car is cond, if, lambda, define, then do special form. Each special form has its own rules for how to do it. Otherwise, it's a procedure call. And so what do? We call apply with two arguments. And here's where it really gets different from the calculator program. In the calculator program, what we gave apply was the name of the function. We gave it the symbols plus sign, minus sign, asterisk, slash. But here we don't do that. We eval the car of the list, the operator, the thing that says what function to call. And the value of it has to be a function. And most of the time, car exp is just a symbol, which is the name of some procedure. We said either we're calling a primitive procedure like, square root or something, or we defined a procedure and we're using the name of that defined procedure as the car of the procedure call. Sometimes, though, it'll be a lambda expression or a call to some function that generates lambda expressions, like my compose function that I showed you back when we did higher order functions, that returns a function. So you can say open paren, compose blah blah, close paren, and then call that with an argument, close paren again. So whatever it is, we evaluate it, and that tells us what procedure we're calling. And then we map eval over cdr exp. Cdr exp is any number of arguments starting from 0 So this doesn't say catter, which would be the second element of the list. It says could'er, which means everything but the procedure that we're calling. So we map eval over those things, and that gives us a list of argument values. Right here where the cursor is blinking, this is why scheme is applicative order. Because remember what applicative order means. It means that we evaluate sub-expressions, argument sub-expressions, before we call the procedure. And what we give the procedure is the values of the arguments, the actual argument values, not the actual argument expressions, as opposed to normal order. If we just said could'er exp here, we'd be doing normal order. We'd be giving apply expressions rather than values. But we don't, so scheme is applicative order. Okay, now how does apply work? Well, there are two kinds of procedures, right? There are primitive procedures built into scheme, and then there are the ones that you create with lambda expressions. The book, confusingly, I think, this is one of the few things I don't like about the book, uses the word compound for two different purposes. So a compound procedure is their name for a procedure you created with a lambda expression, including the implicit lambda expressions in define with parentheses and let. They also use compound to talk about compound expressions, atomic expressions and compound expressions, which means that it's a list that we're evaluating. So compound expression versus compound procedure, they mean two different things. So I try to avoid using the word compound for either of them. So I'll talk about lambda created procedures or defined procedures for that, and list expressions for that. Okay, so there are two kinds of procedures, the ones that are built in and the ones that you create with lambda. So if it's a built-in procedure that we're calling, it works by magic. Do magic. What does that mean? Well, it means what really happens in a real scheme system is that the primitives are written in machine language, or they've been compiled into machine language. And so when we call a primitive, we actually are doing a computer machine language call to something that's in its own native language. You're going to learn all about machine language, by the way, in 61C, a year from now, probably for most of you. A semester from now if you take B over the summer. So we're not very interested in that part of the evaluation process, so I refer to it as magic. What we're going to do in our scheme interpreters written in Scheme is cheat slightly and use the primitive procedures provided to us by the underlying scheme. So we just inherit cons, car, could'er, plus, minus, square root, all of those things from STK. If we wanted to, we could go write each primitive procedure in Scheme in terms of other procedures. There'd have to be a few things that were given at some point. You can't write everything in terms of something else, so you never get the job done. But we could write a lot of the primitive procedures, but there's not much point in doing that. You wouldn't learn anything really from looking at, well, how do we do plus? Although actually a little bit later this week we're going to talk about some aspects of how we do plus. But that's not what's so important. What's important is the evaluation process rather than the primitive procedures. So we're just sort of pushing those under the rug. But we aren't pushing under the rug the evaluation of calls to lambda-created procedures. And in the substitution model, what the substitution model says is we call substitute with three arguments, the body of the procedure, which is an expression that perhaps uses its arguments, the formal parameters, as part of that expression. Second argument to substitute is the formal parameters of the procedure. So these first two things come from the procedure itself. Formal parameters, remember, are the names for the arguments. And then args, which does not come from the procedure, it comes from this expression that we're evaluating, where we said what actual arguments to use. So these are actual argument values. And what substitute is going to do is go through the body of the procedure, and wherever it sees an instance of a formal parameter, it will replace that with the corresponding actual value. Okay? Now, the result of that is something that looks just like the body, except it doesn't have any local variables in it. So if we say, define square of x to be times x, okay? And now I say square of 5, or let's actually not say square of 5. Let's say, just to make it totally clear, square of plus 2, 3. Back in eval, this plus 2, 3 got evaluated. The value of it is 5. And so what substitute does is it takes this body right here and turns it into, or makes a copy of it that says times 5, 5. And now that's an expression that doesn't have any local variables in it. So we pass that as an argument to eval. This is a variable. This asterisk is a symbol. It's no different from symbols made out of letters, except that there's a binding for it. There's a value associated with that symbol when you start scheme up, namely the primitive multiplication procedure. So when eval evals this expression, it gets to that place where it says eval car exp, and car exp is an asterisk. So we go through eval recursively, and we get the multiplication primitive. So that's the first argument to apply. And then the second argument to apply is the list 5, 5 when we do the multiplication. Okay, so this happens by magic, but the invocation of square wasn't done by magic. It was done by substitute. You actually wrote a substitute for homework a week ago, 2 weeks ago. You remember? Anyway, so you've written substitutes. You understand how that works. Your substitute isn't quite complicated enough. I'll show you that when we get to scheme 1. There are some tricky things you have to think about. But basically, what you see on the screen here is a scheme interpreter. And it, fits on a screen. Now, the reason it fits on a screen, of course, is that I left out a lot. So things like look up global value and do special form and substitute all have to be written. And when you put in all those things, it gets longer. So when you look at the actual code, it'll be pretty long. So one of the skills you have to learn, if you haven't already, is how to read a large program. And basically, you do that by taking on faith every part of the program that you're not focusing on right now. So when we do this, when you're looking at what's on the board here, you want to know how apply works, you just take on faith that substitute does what it's supposed to do. You also take on faith body and formals, which are selector procedures for the procedure abstract data type. So in this program, there's going to be a data type called lambda created procedure, and another one called primitive procedure. And lambda created procedures have the selectors, body and formals, that pull out the pieces of that procedure. Okay. So what you don't do, you resist the temptation to go look up body and figure out how that works. You just say, okay, I'll do that later. For now, I'm taking all that on faith because I want to understand apply. That's the trick to understanding a large program. is you just believe every part of the program does its job except the part you're looking at, and that's where you focus your attention. All right, so now here's the actual Scheme 1 program. I should show you how it works. So you say load total CS 61A slash lib 61A slash lib slash scheme 1. You spell it right. It works better that way. It says OK. And you say scheme -1. And you get the scheme 1 prompt, into which you can type expressions like +2, 3, or lambda x times xx applied to 5, and so on. So that's scheme 1. When you want to leave scheme 1, all you do is you type something that isn't a valid expression like that, and you get an error message, and you're back in STK. OK. So here's the read eval print loop. As in the calculator program, there's this call to flush here, which just says, even though I haven't printed out a new line character, actually print the stuff anyway, because I want the user to see it right now. And then we have read an expression. Read is also something that we get from the underlying STK. So there's an STK procedure called read, which we're using here. That's the thing that takes the sequence of characters that you typed that's full of things like digits and letters and spaces and parentheses, and goes through it character by character and turns it into essentially a box and pointer diagram for what you typed. And that's what read returns. And then we call eval of that expression, except we actually call it eval1. And we also use apply1. The reason for that is that STK itself has procedures called eval and apply that are user visible. And we don't want to override its definitions. So we called ours something different. So eval1 of read, and then print whatever eval gives us. And then here's the loop part of the read eval print loop, call scheme 1 recursively. Questions about the REPL? So if you're a Lisp maven, everybody who's a Lisp maven knows the word REPL. It means this code right here, read eval print loop. OK. This file has voluminous comments, as you can see. Comments, 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 comments. So you'll be reading all that, because you're going to work with this in homework and lab this week, I believe. Actually. So here's all of eval. And it's a little bit bigger than the one-screen version. So constant question mark, that's the same as self-evaluating question mark. If it's a self-evaluating expression, return the expression. If it's a symbol, then we call eval. Note, not eval1, but eval. The reason we do this, remember I said, by the time we actually see a symbol in eval as something to evaluate, it has to be a global variable, not something that's an argument to a procedure that's running. And we let STK handle our global variables for us. In particular, this means we have access to all the STK primitives, because all of the names of primitives, since they're symbols, we pass on to STK to eval for us. That's the main reason that we have global variables at all, is in order to have access to the primitives. So that's a little bit of a cheat, but not too much. In the metacircular evaluator in chapter 4, we don't cheat in quite that way. And then, instead of something that says special form question mark, exp, we have a con clause for each of the special forms that are implemented. In Scheme 1, there are only 3 special forms. And they are, quote, if, and lambda. Quote's important to get data that isn't self-evaluating into our system at all. As I hope you know by now, here we go. When you say quote foo, the read procedure translates this into this special form. So the quote symbol is just an abbreviation for this. It's a special, so quote is a keyword. Quote foo is a special form. The value of quote foo should, of course, be foo, which is the catter of the whole expression. So expression is quote foo. The value of that is the catter. And that's what we do on this line where the cursor is blinking. How about an if expression? So if, remember, takes 3 arguments, one that's true or false, and then what to do if it's true and what to do if it's false. So we use STK's if to make this decision for us. Is that a problem? Is that a circularity? Are we going to get in trouble? We're going to be doing eval of this if expression over and over again? No. Because the expression that we're evaluating is a Scheme 1 if expression. This expression that you're looking at, although it's part of the program that interprets Scheme 1, this program runs in STK. So this is an STK if you're looking at. So we use STK's if to help us do our if. But STK's if doesn't do all the work. We don't just take the whole expression and pass it on to STK. We can't do that because part of the job here is evaluating sub-expressions, and it has to be done with eval 1 because they're Scheme 1 expressions, not STK expressions. But we do use STK's if. What does STK's if do? Well, it always evaluates its first argument. So we start by eval 1ing the first argument to if, cat or exp. And then depending on whether that comes out true or false, we do either eval 1 of the catitor or eval 1 of the cateditor. So Satish told you have to learn how to pronounce these things, and you do. Notice that we only do one of these. So our Scheme 1 if has the same property as STK's if, that it doesn't evaluate both the second and the third argument. It only evaluates one of them. And that's important, as you learned in the first week's homework, I think. There was the exercise about new if and why new if didn't work. If you're going to write recursive procedures, you have to not evaluate the recursive case if you're in the base case. So that's why it's important that if is a special form. And our if indeed behaves correctly. Okay, next comes lambda. This may be a little surprising. A lambda expression's value is the lambda expression itself. So in a substitution model scheme, we can represent a procedure as the lambda expression, because all we need from it is the formal parameters, which is the catter of a lambda expression, and the body, which is the cateditor, sorry. The third element of the list will be the body. This will not be true when we get to the metacircular evaluator. In a couple of weeks, you're going to learn about a different model of evaluation called the environment model, which is more complicated than the substitution model. And you'll see in the environment model that we can't just represent the procedure with the lambda expression, that we need more information than that. But in this interpreter, we can, and so we do. Notice, by the way, that define is not one of the special forms here. So in scheme 1, we can't make definitions of new things. Kind of interesting. So if you want to write recursive procedures, you have to do it using the trick that was the extra for experts a while back of the Y Combinator, where you manage to have a procedure have itself as one of its arguments and do recursion that way. It's the only way to do it in this evaluator unless you invent a defined special form. OK. So if it's not quote or if or lambda expression, and it is a list, it says pair question mark here. And that's just because it's not a valid expression if it's a pair unless it's a list. And we don't actually bother checking, because in general in this class, we don't do a lot of error checking. That's 61B. And pair question mark is theta of 1 time, whereas list question mark is theta of n time. So it's a tiny optimization. Probably shouldn't have done it that way. Anyway, there it is. So suppose that the expression we're evaluating is a list, and it isn't a special form. In that case, it's a procedure call. So you've already seen what we do. We call apply 1. And the first argument to apply 1 is eval 1 of the car of the expression, which tells us what procedure to call. And that could be a global variable a lot of the time, or it could be a lambda expression, the value of which is, as we just saw, the lambda expression itself. And then we map eval 1 over the coulter to get the actual argument values. So what you see here is exactly like what you saw in the tiny one-screen version before. If it isn't any of those things, it's an error. OK, so then comes a lot of comments about apply. Oops. And here is apply. Oops. So remember, in the one-screen version of apply, first thing we did was test to see whether the procedure we're trying to call is a primitive procedure or a lambda-created procedure. We do the same thing here. It doesn't look as if we do the same thing, because it doesn't say primitive question mark here. It says procedure question mark. So this is where you have to bear in mind that scheme 1's primitives are STK's procedures. Anything that's an STK procedure, we take to be a primitive procedure for our purposes. So you can define a procedure in STK and then use it as a primitive in scheme 1. So therefore, since our primitives are procedures of STK, to call them, we can just use STK's apply. And again, notice this is not a call to apply 1, which would be scheme 1's apply. It's a call to apply, plain old apply, which is STK's apply. This business about scheme 1 versus STK, I realize it's confusing. It's going to take you some time to think this all through. It would be a little easier if we were writing an interpreter for some other language. If we wrote an interpreter for, BASIC or Python or something, Perl, if we did that, then it would be clear to you the difference between scheme code and code in the language we're trying to interpret, which would look very different. Here, the language we're trying to interpret is the same as the implementation language. They're both scheme. They're a little different because, for example, scheme 1 only has 3 special forms. STK has a lot more that you know about already. A couple that you don't, coming up later. So there are differences, but they're subtle differences. Whereas if we were interpreting some other language, then the differences would be much more dramatic, and it would be easier for you not to get confused between using, for example, scheme 1's apply versus STK's apply. That kind of issue wouldn't arise for you. So why don't we do that? Why don't we pick some other language to interpret to make things less confusing? Well, because 2 reasons. One is there's only one language that we know all of you know. Okay, so I don't want to have to teach you another language just so that we can write an interpreter for it, although we're going to do that actually later in the semester when you write a logo interpreter. But we picked logo because it's much closer to being scheme than some of those other choices would have been. So that's coming later, but for now, we want to use a language you already know to make things simpler in that way. But there's another reason too, and this is really interesting. So we have in an interpreter, here's the interpreter, and it's written in an implementation language. And what we put into it is in some potentially other language, which is the source language. And let's say you're teaching a class like this, and you want your students to write an interpreter that's going to be as good as possible, but have it be as easy as possible to write. So you want to have an interpreter for some language, and you want to make it really easy to write the interpreter. Okay? So what languages would you pick? Supposing you had the whole universe of languages available to you, what language would you use as the source language, and what language would you use as the implementation language? It's tempting, it's very tempting to say that for the source language, you really want something trivial and babyish. So maybe we're going to write an interpreter for BASIC, because that's a tiny little language, fits on 8-bit micros like we used to have before you were born. So let's use BASIC as the source language. And for the implementation language, you want a really powerful language that can do anything, can handle text processing and list processing and do all kinds of computations and make it possible to write an intricate program fairly simply. And so maybe you would pick something like Java as your implementation language in order to get the easiest possible write an interpreter assignment. Well, it turns out that that's wrong. It turns out the easiest possible write an interpreter assignment, just trust me about this for now, as you grow and learn more languages and actually write interpreters and compilers, which you're going to do if you take 164, which I recommend, it's the compilers course, you actually will do things comparable to writing a compiler for BASIC in Java. But that'll be much, 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 much harder. The easiest possible interpreter in the world to write is scheme in scheme. That seems a little counterintuitive. It seems like you want this language to be trivial and simple and not very powerful. You want this language to be big and strong and industrial strength and can do anything. How is it that these can be the same language? It's because, well, partly it's because of lambda, which turns out to be very, very helpful. in general, it's because Scheme is a language that can do a lot, but it has a very uniform notation. You already know that. All the expressions look the same. And if you've programmed in other languages, you know, 1 week you learned about the if statement, which has a such and such notation. And then the next week you learned about the for statement, which has a different notation. And then the week after that, you learned about the print statement, which has yet another notation, and so on. In Scheme, there's only one notation. It's parenthesis, blah, 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 close parenthesis, right? No matter what you want to do. So Scheme is a very simple language to interpret. Also, not only is Scheme a powerful language in general, but it's particularly good because it's a flavor of Lisp, which remember stands for list processing. It's particularly good at lists. And what is a Scheme program? It's a list. The notation for lists of data, you know, ABC, whatever, is just like the notation for procedure calls or anything else. So Scheme has the tools that it needs to handle Scheme code very easily. And that's another reason why writing Scheme in Scheme is so simple. And that's the reason I promised you back in week 1 that I would tell you why the notation was f, x, y instead of f parenthesis x comma y. Remember I promised you that? This is why. It's because one chunk of a Scheme program is a list, a Scheme list. So we call eval, if the notation were like this, we'd call eval with a big mess. Instead, we call eval with one expression, which is one list. And we can do car and coulter on that expression. So that's one of the things that makes Scheme so easy. And there's a big, long story about the history of Lisp. In the very, very, very early days of Lisp, when it was just an idea in the head of John McCarthy, he actually used a notation that was more like this. But the reason he wanted to invent a new language was to do reasoning about programs. And so he said, well, when we're using a program as data, we'll write it this way. And this was called an M expression, and I forget what the M stands for. And this was called an S expression for symbolic. And for a long time, the Lisp documentation had both of those things in it. But when he handed off this idea to one of his grad students and said, here, actually, you know, make a Lisp that works, the grad student said, oh, God, this is really hard. And what he happened upon was that there already was that tiny thing that I showed you, the one-screen Scheme interpreter. There was a Lisp interpreter like that McCarthy had written as documentation for how it should work. And he said, well, if we just use S expressions all the time, then I can just use that code as a model. And so there aren't any M expressions anymore because it turned out to be so easy to do it this way. OK. I have 1 minute. So here's substitute. There's a big comment about substitute. And here it is. And as you see, it takes a little more than a screenful to do it all. When you read this code, don't spend a lot of time on substitute, because this is the part that's a lie in terms of how Scheme really works. The code is a little tricky, and the reason it's tricky has to do with the following fact. What if you have a procedure with an internal definition inside it? So there's a lambda inside the body of another lambda, and they both use the same formal parameter, x, because it was written by one of those programmers who calls everything x, you know. Well, when we do substitution in the outer one, we have to protect the uses of x in the inner one from being substituted, because we don't want to substitute for those until we actually call that inner lambda. So a lot of the complications in here have to do with that. And the real Scheme, as you'll see, doesn't do anything like that at all. So I want you to focus your attention mostly on eval and apply as you read this, which you're going to for the lab and homework. Thank you.